Well, thank you for inviting me. My confession is I'm not a biologist. I can't really tell you anything about trees. My wife can, but not me. But I will be telling you about what's happening to our climate system and why that is so important to us and our children and our grandchildren as we move forward. So what I'm going to try to do is give you a little bit of insights to what's happening with the Earth's climate system in terms of what our recent assessments have told us. So one of those assessments, and I led chapter 1 on the IPCC assessment. This is an international body that brings together the scientists every 5 or 6 years to assess our understanding of the science. So it pulls together scientists from all over the world to try to do this, and over 300 authors, 250 some authors on, well, that was the previous assessment. The current assessment, I think, is closer to no, that is the recent assessment, sorry. There's about 300 authors total by the time we added a few others along the way. And this is a very extensive process. It's we don't get paid for this, by the way. It's just something the scientists do because this is an important issue that we offer our time. And it goes through a very extensive review process. Similarly, the U.S. National Climate Assessment, and we just completed the third one. We released it in May. So we released that IPCC assessment last September. And then very recently, the synthesis report came out because there's 3 different working groups. So that report I was showing you was the science of climate change. It's about 1,000 pages. And there's a similar 1,000 pages on the impacts of climate change, and another 1,000 with another whole different set of authors, and another 1,000 pages relating to policy options and policy considerations and economic analyses. For the U.S. National Climate Assessment, which is supposed to be done every 4 years according to the law that was passed by Congress in 1990, but that didn't happen. And this is actually the third one that was just published. We published the previous one in 2009. The intention was to, at that point, to try to really start doing these every 4 years, since Congress had wanted that, to bring together top scientists and other experts from around the country to try to assess our understanding. We had about 300 authors, went through a very extensive review process, 2 analyses by the National Academy of Sciences as part of the process, peer review, public review, and so forth. None of which changed any of the arguments, basic arguments in of the science. But what they did do is make the language very clear, because this is intended to be a document for the public, whereas that IPCC assessment is really an assessment, really an analysis done for other scientists. And then there's a policymaker's summary that is more intended for policymakers. You can get the assessment from nca2014.globalchange.gov, and I suggest you all look at that. There's 870 pages total. There's a summary there's a highlights that I've given to a few people here, and then there's a overview that I've left on a table in the middle here by the projector that it won't be enough for everybody, but if you want one, just send me an email. I'll be happy to send it to you. But you can also get all that information off of the website. So what do these assessments tell us? We used to talk about climate change as something that's in the future, something we need to be worried about because it's going to be affecting us. Well, the future's now. We're finding that climate change is already affecting us. It's affecting people throughout the world, but it's also affecting people here in the United States. And it's having an impact. And we'll go through some of the evidence for that already. As Jerry mentioned, it's also occurring very rapidly, over 10 times more rapidly than the climate has changed since the end of the last ice age, anytime since the end of the last ice age. Climate has changed dramatically over the millions of years of life being on Earth, but it usually changes very slowly. usually over thousands of years. Now we're seeing major changes occurring in decades. And it doesn't just change to be changing, it changes because there's a forcing on the climate system. And so, and we can look at those past time periods and explain what was going on with them as based on what evidence we have. But we also know, as I'll show you, that the primary evidence, the major evidence, indicates that what we're seeing now, the changes we've seen over the last 5 decades, is due to human activities. So this kind of a busy graph, the upper left-hand side shows the many, many thousands of observations of temperature taken around the world every day, and shows you that there's been about a 1.5 degree Fahrenheit increase in temperature over this time period. There's multiple analyses of all those data records because they want to make sure every group, and there's 3 groups there. There's actually a 4th one in Japan, and actually a 5th one at UC Berkeley, that have analyzed all these data records and basically come up with the same conclusions. They disagree a little bit as to what stations should be kept and which ones shouldn't in some cases, and so there's slight differences. But the basic conclusion is that we're seeing this 1.5 degree increase, and most of that increase, the majority of that increase, has occurred in the last 50 years. In a time period when it cannot be the sun that explains the observed changes. And in fact, it lines up very well with what we expect from human activities and some effects of natural variability in the system that causes some slowing down at certain time periods. And we can talk about that. If you look in the right-hand side, on the upper right, and then for the northern hemisphere, where we have the most data from proxies, we can go back 2,000 years with pretty strong indication of the year-by-year changes in climate. With some uncertainty. Certainly the uncertainty goes as you go further back, which is indicated by the gray, gets larger. On top of that is the red, which is this temperature record from the right, and shows you how rapid that change has been. And if you look at the last decade, this is the warmest decade, and I'll show you a graph of a decadal analysis of temperature in a minute. But the last decade was the warmest decade in this last at least 1,400 years, but probably more like 2,000 plus, as we go back over human existence. But temperature is not the only indicator of a changing climate. There's many, many other indicators. So it's not just surface air temperature. It's we're seeing the oceans are increasing at essentially the same rate. Upper levels of the ocean particularly. The ice around the world is generally decreasing. Over 90% of the glaciers have decreased dramatically. Sea ice in the Arctic has decreased extensively. And humidity in the atmosphere has increased. A warmer atmosphere holds more water vapor. We can observe the increase in water vapor in the atmosphere. And on and on. So there's many, many indicators. These are just a few of them that indicates the climate is changing. This is the decadal record. In the last 5 decades, we've seen a continual increase in the temperature. When we start talking about climate, we're more like climatic timescales, because weather is the short-term variations in the Earth's system. The climate is the longer-term averages and statistics of weather. Usually we go over 20, 30-year time periods. But nonetheless, the decadal is a nice indicator of the kind of changes that are occurring. If you look at the temperature record around the planet since 1901 to 2012, and I need to get an update of this, it's just when the IPCC assessment analysis ended, so it's the only graph I have of it. The white area is where we just don't have enough data to tell you what was going on there. Although if you fill that in based on other information we have, you actually find that the largest changes are actually going on near the poles. They're warming at a much more rapid rate than at mid-latitudes or in the tropics. But nonetheless, the orange, the red, the purple areas are all in areas where we find very extensive warming going on throughout the world over this time period. You'll see there's a couple of areas where there's been very, very small changes, even slight cooling, such as the area off of Greenland, where we're getting all this fresh water into the oceans from the melting of that sea ice I mentioned, and also from land ice from Greenland that is actually affecting ocean circulation a little bit and is causing a slight cooling effect. And then the other area that kind of stands out is actually in the southeast. And there's been questions as to what's going on there. Is it related to changes in the weather patterns, which could be part of it, or is it related to the fact there was heavy deforestation early in the century, followed by forestation that has helped keep that somewhat cooler in that region. And we're still trying to sort all that out. But overall, clearly the planet has been seeing a major change. This is just looking at the US in more detail. As you go further north, we expect that there should be a larger change, and that's indeed mostly what's occurring. And you can see the generally warming everywhere except for a couple states in the southeast. Turning to precipitation, generally we've seen an increase in precipitation. I already mentioned the fact that a warmer atmosphere holds more water vapor. It should lead to somewhat more precipitation, particularly what's going on is, in a general tendency, is the wet get wetter and the drier get drier. Generally a drying in the subtropics, for example. And that is clearly showing here where the southwest and the southeast are generally getting drier, even though the southeast started out a lot wetter than the southwest. Well, it isn't just temperature, precipitation, these small changes we're seeing that. In fact, that's the least of our concerns. Much larger concerns is that Americans are already feeling, and people around the world are already feeling the effects of increases in certain types of severe weather, and in particular, an increased intensity in severe weather. And also in sea level rise. We'll talk about that a little bit later. So generally, heat waves are increasing across the US and much of the planet. Not so much here in the Midwest, but through much of the rest of the nation, we're seeing an increase in heat waves. Cold waves are generally decreasing. Doesn't mean you can't have a cold winter like we've had this last winter, but that has become much, much less common over the last 30, 40, last 50 years than it was before. More precipitation is coming as larger events. So when we get a rainfall or a snowfall, it's more likely to be larger than it was before, in part because of the fact that the atmosphere holds more water vapor. And so when you get the right kind of storm system, it dumps. And so we've been clearly seeing that throughout most of the nation. The only real exception to that is Hawaii. And we're still trying to sort out what was going on there. But if you go look at most of the world, we're actually seeing the same thing, that more precipitation is coming as larger events. As a result of these changing patterns in temperature and precipitation, we're also seeing an increasing risk of floods in some regions, particularly the Northeast and the Midwest, based on an analysis by the U.S. Geological Survey from a couple years ago. Droughts are increasing in certain regions where where it's tending to be drier, the Southwest and Southeast in particular. Increasing intensity of Atlantic hurricanes is occurring over the last 30 years and is likely to continue. That doesn't say anything about whether they hit land or not. It's just a matter that a hurricane is likely to be more intense. And all these trends are likely to continue. There's some things I don't say up here, such as tornadoes, and initial analyses we've been doing suggest that tornadoes are likely to become more intense and perhaps more numerous, but it's too early to make strong statements about those. We're still doing the research. I'm hoping that one of my students is going to have a nice paper on that out within a year. And we can say the same thing about ice storms and hailstorms. We know that something's going on. If you look, and we could do this globally as well in the US, I'm just going to show you in the US, but since 1980, NOAA, National Oceanic Atmospheric Administration, has been tracking what are called the billion-dollar events. These are just the events, weather events that cause damage greater than $1 billion. So they don't as carefully track those that are maybe only $100 million. But nonetheless, we've seen an increase in the number of such events over time, and we've also seen an increase in the amount of dollars that it's costing the American people. And there's many different types of storms. So you can see that all parts of the U.S. are really being affected. So these show you things like droughts and floods and hurricanes and wildfires in the West and severe local storms, etc. Now, if you look at that the last few years have all been over $100 billion in terms of cost to the American people through affecting our taxes and affecting recovery of those areas. And you compare that with things like the U.S. Department of Education, which gets $60 billion a year total, or the U.S. Department of Transportation, which gets around $80 billion or so, then you see this is really a pretty important change in our climate system and how it's already affecting our economy. I mentioned earlier the change in heavy precipitation. This just shows the data from the top 1% of the events over the last 50 years in terms of the change in the, so if you go back 50 years ago and say, what were the top 1% of events that were occurring in the precipitation before then in each region of the U.S. We broke the U.S. up into various regions. And what you find is the largest change is occurring actually in the Midwest and the Northeast, which has been very significant in terms of that increase in precipitation. Now, why are all these changes occurring? To understand that, you need to go back to some basic physics and what's called the greenhouse effect. Greenhouse effect was discovered in the 1820s by a famous mathematician and scientist called Fourier. Anybody with a science background would have heard of the Fourier series or the Fourier transform and many other things that Fourier did. He was really quite an outstanding person. Well, he had this idea that, which has been determined to be exactly right based off of many measurements since then, that solar radiation largely penetrates the atmosphere to the Earth's surface. Because of the albedo of the Earth, the reflectivity of the Earth, about 30% of that radiation goes back to space, and there's a little bit absorbed in the atmosphere, but most of that radiation reaches the Earth's surface, and because of the size of our planet and and particularly its temperature, that radiation is re-emitted. It can't just stay absorbed in the Earth, it has to be re-emitted. Again, basic physics. And because of the temperature of the Earth, it will be re-emitted in infrared wavelengths. Now, if that radiation went back to space, then this would be a frozen planet, and we would not have life as we know it. But it's because of certain gases in the atmosphere called greenhouse gases, water vapor being a key one, but also as another key ones are carbon dioxide, methane, nitrous oxide, ozone, and several others. Because those gases are in the atmosphere, they absorb that radiation, that infrared radiation. They re-emit the radiation, and some of it ends up being trapped in the Earth atmosphere system. It's like a blanket going on, like when you go to bed at night. When you put a blanket over the Earth, and it keeps the Earth warmer. Unfortunately, what's happening is because of our burning of fossil fuels and land use changes, we have increased the amount of carbon dioxide in the atmosphere, and I'll show you that shortly, and the amount of methane, and the amount of nitrous oxide, and some of these other gases. As a result, it's like adding an extra blanket. The Earth has to warm. The basic physics of what's called climate change, or the media likes to call global warming, is essentially that simple. Everything else is a detail. We also know from many past studies as I mentioned earlier, it requires a special forcing on the climate system to get a really major change in climate. We know that every 100,000 years during the last 2 million years that we've had an ice age. And that is clearly connected with what's called the Milankovitch effect, or Milankovitch theory, which takes into account the orbits of and eccentricity, et cetera, of the Earth as it goes around the sun. And at the right combination of those, of 3 different parameters, then you should go into an ice age. And so we came out of the last ice age less than 20,000 years ago, and slowly we will be entering, very, very slowly, we'll be entering another one, over the coming next few thousand years. We also know that, of course, very important to the Earth's climate system is whatever output there is from the sun. And the sun has played a major role in terms of what the climate has looked like in the past as it's gone through various cycles in itself and in terms of its output. But the problem is since 1978, now we have a pretty good understanding of what's driving the sun and there are various models of the sun. But on top of that, since 1978, we've had very accurate measurements of the solar output. And actually, they show that, if anything, we've had a slight decrease in the output since that time period, not an increase. So that can't explain the increase in temperature that we've seen, or the changes in climate. Stratospheric aerosols from large volcanic eruptions that can emit very large amounts into the stratosphere, explosive volcanic eruptions, the sulfur in those sulfur dioxide gets converted to sulfuric acid aerosols, and that can reflect sunlight. Sulfur from coal burning power plants does the same thing, but it doesn't last as long. So for volcanic eruption, it emits into the stratosphere. The sulfur can stay there for several years and cause a net cooling effect on the Earth's surface, whereas the sulfur from coal burning is only lasts in the atmosphere for about a week or so, a week or two. And so it doesn't have nearly as large an effect. It's still important. And if I were doing a complete analysis of climate change, I would show you that, but I'm not going to do that today. On the other hand, we've also learned particularly the last century now, because the first idea that climate could be changed by an increasing amount of carbon dioxide came from Arrhenius, Svante Arrhenius, a very famous Swedish chemist, to propose that if CO2 could increase, it would probably change the climate. And he actually calculated through a simple rate of transfer model just how much it could change. And he was about right, within ballpark. And that was 100 years ago, in the 1890s. Well, we know that from many analyses since that the increasing amount of carbon dioxide in the atmosphere or increases in methane and other gases can have an impact on the climate system. This shows the carbon dioxide measurements made at Mauna Loa Observatory that were started by Charles David Keeling. Dave Keeling is a graduate of Illinois, so I'm always proud to say that, and then worked for worked in UC San Diego for many years. And he developed a very accurate instrument for measuring carbon dioxide. It's now, versions of that are still used around the world in a number of different places. But it ends up Mauna Loa Observatory in Hawaii actually kind of well represents the average amounts around the planet. CO2 is very long-lived in the atmosphere, has a very rapid exchange rate with biota, but after allowing for that exchange rate, its lifetime is in the order of 100 years. And then the second lifetime is much, much longer. And this is part of the problem, thousands of years. And so we're going to leave a legacy for many generations of the emissions we're making into the atmosphere right now. But you can see the very dramatic increase we see in CO2. You can also see the breathing of the biosphere. If you look at the annual variations there, which I won't go into here, but obviously strongly related to trees. And other gases have also dramatically increased. The amount of methane in the atmosphere has almost tripled over the last few centuries. for example. Particles are also important. Some of those particles cause cooling effects, like the sulfates I mentioned earlier, but there's also black carbon, which also can cause a warming effect, for example. A little bit more about CO2. This shows you an ice core of carbon dioxide going back where they trapped the, you can measure the amount of carbon dioxide trapped in bubbles in the ice in Antarctica, from Antarctica. And as I said, it's long-lived, so it gets pretty much the same amounts throughout the world. And you can actually see the ice ages. You can see that CO2 was much less concentration during an ice age than it is in between. In between, it's about 280 to 300 parts per million. During an ice age, it's about 200 parts per million, but now it's over 400 parts per billion. 400 parts per million, the last time we saw that on Earth was about 1.5 million years ago, when it was a much, much warmer Earth than it is now. CO2 is a strong driver of the climate system, along with water vapor and other things, like I mentioned earlier, and this is an important change. By the way, that change in CO2 you see there, which is largely connected with the ice having an effect on the biosphere, is also a strong driver of about half or more of an actual ice age. The decrease in CO2 plays an important role. Now, there's many different types of analysis of attribution, of why we say it is human influence that is driving the changes in climate. I'm not going to have time to go into all that evidence. I'm just going to show you one quick example. This is from the IPCC assessment. If you looked at the observed changes in temperature from 1951 to 2010, so over a 60-year time period, it's about 0.6 to 0.7 degrees centigrade. Multiply that by about a factor of 2 to get Fahrenheit. And that observed change is shown at the black line up there. Now, I mentioned all those increases in the amount of these greenhouse gases, carbon dioxide, methane, nitrous oxide. That would drive a forcing that by itself would tend to have said, oh, we should have seen a temperature change larger than that. But that's counteracted by the fact we're putting all these particles in the atmosphere, these sulfates from coal burning, for example, and other particles that are prevented by human activities. Overall, those have a cooling effect. And if you add the two together, you get the anthropogenic component, the human-related component. And you see that can almost exactly matches the changes in temperature that were observed. I already said that the solar influence was minor, essentially zero during that time period, and volcanic eruptions. This has been a pretty quiet period, particularly relative to the 1600s, 1700s when we had the Little Ice Age, which best evidence indicates was not a solar effect. It was actually, is often stated in media as being related to sunspot cycles, but it actually was related to a number of very large volcanic eruptions during that time period. Internal variability is also important in short timescales, but that cannot explain this kind of change over this time period. The best explanation, by far, is that it is human activities driving the change during this time period. As a result, IPCC concluded it is extremely likely, that means it's greater than 95% probability, because we tend to be kind of conservative. We don't want to say it's 100% probability at this point yet, that human influence has been the dominant cause of the observed warming since the mid-20th century. If you look at the projections into the future, this just shows you two examples. There's a number of different scenarios that have been looked at. The scenarios take into account population change, economic development, family lifestyle, a number of different things go into their assumptions about how these gases will continue into the future. A lot of it, of course, largely depending on what we do with our energy and transportation systems. And the largest case here, which is not as large as it could be because it still assumes a significant fraction going into renewables, basically assumes that we continue to heavily use fossil fuels. Whereas the blue, the lower case, assumes that by 2050 we start moving strongly away from fossil fuels. In the most recent scenarios, there's also even lower ones where we look at various policy options. And the idea is trying to get below 2 degrees centigrade, so 3.6 Fahrenheit, trying to get something below that is very, very difficult. And that's the kind of thing that some of the policy-related analysis are looking at. Looking at the US for those two scenarios I just showed you, the high case means on an annual average, more like 9 to 10 degree change Fahrenheit increase for the US. Get a feeling for what that means. The last ice age was about 15 to 17 degrees cooler than the current climate. So we're talking about a warming that's approaching that kind of magnitude. That's very, very large compared to what temperatures have been like on Earth. And this is annual average, so you're going to expect that we're going to get larger changes in the summer than in the winter. For the lower case, which is hopefully what we do follow, or something better than that, we're talking about 3 to 5 degree Fahrenheit increase. It's still significant, it's still going to have a major impact, but much less so than the higher case. We'll still have to adapt to the changes occurring in climate, and that includes urban environments and our forest. Turning to precipitation very quickly, the teal and bluish colors tend to indicate where we expect an increase in precipitation, typically in the northern latitudes. Midwest, we expect wetter springs and winters, but summers tending to be drier throughout most of the nation, and falls maybe slightly wetter in our region. If you live in the Southwest, though, significant drying through most of the seasons. To give you a feeling for what this is about, this shows an analysis I developed some years ago, about 15 years ago, called Migrating States. It just shows where Illinois, in this case, kind of ends up in terms of its climate for a summer. And so this is looking at the average summer temperature and precipitation compared to what's going on now. And so we become, with the high case, maybe more like eastern Texas. Well, that's if you've ever been to Dallas, you know that there's summer. I have a son who lives in Dallas area. I won't go into all the stories I have about that, but he's been seeing, essentially a month of 100-degree weather, typically 20 or 30 days, and most of the summer being above 90 degrees. And that's very different than the climate here in Illinois. So, but even in the lower case, we're still talking about a very different climate than we're used to, and something we're going to have to adjust to. Turning to sea level rise, we've seen about an 8-inch increase in sea level over the last century. That's already affecting a number of cities throughout the country. For example, if you look at Miami or Norfolk or a number of cities along the East Coast and also cities along the West Coast, when you get a high tide these days, it's flooding the streets at times. A really, a fairly high tide, and that wasn't seen several decades ago, but now it is becoming much more regular as the ocean levels continue to increase. Over this century, we expect another 1 to 4 feet. The amount really depends on the melting occurring in Antarctica and Greenland. And if we're wrong, it could be much higher. There's been some suggestions it could be as high as 6 feet or more. But best analysis right now are 1 to 4 feet. That will have a very significant impact by the end of the century on many of our coastal areas. And this just shows the southeast area in terms of vulnerability. On top of that, storm surge is very important. This shows Sandy in New Jersey, and the fact that storm surge is just as important to creating damage as sea level rise. And that can also be very important, by the way, to agriculture, as has been shown in a number of cases as well. On top of that, this carbon dioxide we're putting in the atmosphere, about 25% of that of that carbon ends up in the oceans. In the ocean, CO2 converts to carbonic acid, and carbonic acid will then make the oceans more acidic. The oceans are basic, but they are becoming less basic, and that's called acidification. And the effect of that over time is that shellfish are likely to decrease in size. Number of small ocean animals are likely to be affected. The total effects on the ecosystem of the oceans is still not understood, but it could become quite important. Well, these analysis we did for the National Climate Assessment, and similar analyses done for IPCC looking at the planet, have shown that the resulting impacts of many different sectors. Sectors, people here are going to be interested in, like ecosystems and forestry, but also in human health and agriculture and energy, transportation, et cetera. I won't have time to go much into that, but I'll touch on it. Americans are already seeing impacts across all of these different sectors. Looking at something like human health, climate change threatens human health in a number of different ways, including extreme weather events like I talked about before, and wildfires, decreased air quality, more concerns about ozone, for example, and diseases transmitted by insects, food, and water, which are more readily moving around the world. One thing I'm really concerned about, because I have bad allergies, is the fact that ragweed pollen is already increasing as a result of the being warmer. But in 2008, I led the assessment of climate change for the city of Chicago, called the Chicago Climate Action Plan. And in that, we were asked, one of the key concerns that the city had was, well, what about the 1995 heat wave? It resulted in 800 plus deaths in this region. How likely such an event be? What our analysis suggested, using the best modeling capabilities we have, using downscaling techniques, et cetera, we came to the conclusion that what was uncommon will likely become common over the coming decades. And as a result, the city of Chicago started adaptation measures. And they started looking at how we could warn people about a heat wave coming. Heat wave, being a week-long event at least, that are on the order of a week or longer, with 100-degree days in there, warm nights, et cetera. And the elderly and the poor have very difficulty adjusting if they can't get to a cooler sheltering place. And so the cities worked hard on that, and as a result, when we had a significant heat wave in 2012, instead of 800 deaths, there were 20. And so it already had some impact on this region. Water resources, which is a big concern to ecosystems, is water quality and water supply are being jeopardized by the climate change in a variety of ways that affect ecosystems and livelihoods. That's maps I show. So analysis of regions that are in risk based off of there being no climate change, and then and this is an estimate for 2050, and then including the effects of climate change on top of that, and what that means both to the local water supply and to effects on what's happening with the use of aquifers, et cetera. Much larger areas of the country being jeopardized as a result. Agriculture, over the next few decades, we largely don't expect a major impact, but over time, the warmer temperatures leads to more stress on the plants, potential decreases in yields, and in fact, there's already papers coming out that's showing that despite the increases in yields in the U.S. because of continual improvements in the genetics of these plants, that worldwide there's already a decrease occurring in production. Over time, agriculture faces challenges from the heat stress, water stress, pests, diseases, and weather extremes. Weather stress can mean not only just concerns about droughts, but it can also mean there's too much water coming as precipitation in flooding the fields in the springtime when farmers are trying to get out and plant the crops. And that's actually become more of an issue in central Illinois in the last few decades. Turning more to the urban environment, there's a number of things we could talk about in terms of infrastructure. Just show you one example. Generally a decreased demand for gas and oil for winter heating. And this is analysis that were done for Chicago, again, the Chicago Climate Action Plan, but compensated for by a significant increase in demand for summer cooling. If we turn to ecosystems, as we already heard from Jerry, trees don't move very rapidly. And as a result, forests are in jeopardy, and particularly in the Midwest and the Northeast, hardwood floors that may have a lot of trouble adapting to this extremely rapid changes occurring in the climate system. Other animals and plants may be able to adapt, but there's a lot of analysis still going on that suggests even they are likely to have some issues. Overall, as the amount of temperature change gets larger, if we follow the higher scenario versus a lower scenario, then the risk in all these different sectors become more important. There are many actions we can take to reduce future climate change and its impacts. That's mitigation. But also we need to prepare for the impacts we can't avoid, and that's adaptation. And there's many possible ways of doing that. I won't go into all that here. We do know that future climate change does depend particularly on the emission levels of those gases that I was talking about, carbon dioxide, methane, et cetera. I do want to leave you with a sense of hope, because I think when I talk about climate change, it's pretty depressing. But the reason I give all these talks is because I'm really concerned about our children and our grandchildren. Our future does depend on how we act to deal with this issue. The science is very clear. You may sense that there's this big debate going on in the media. There is no debate in the science community itself. If you look at the peer-reviewed literature, which is how we judge ourselves, look at the journals and the analyses, like these synopses that are done as assessments, the message is very, very clear. Adaptation's not a choice. Our choice is whether to adapt proactively or just respond to the consequences. Adaptation requires a paradigm shift. We need much more focus on managing risk as we go forward. But I also feel that we as Americans, or we as people of the world, can draw on our long history of responding to changing conditions and facing these challenges before us. We can deal with this. I feel confident of that.